Good afternoon.
Hello guys, nice to see you.
Hello.
How are you doing?
Hello.
I'm fine.
Good.
Good afternoon.
Hello. Nice to see you. Good afternoon. So guys, you remember that you have some important event tomorrow?
Yes.
Yes, of
Mhm.
course.
Good. So please take care that your internet connection is good and also take some time. So log in a little bit earlier to the system prior to the beginning of the midterm in order to avoid some possible technical issues. Also, when you get your problems, please read carefully all of them. That's very important because you need to identify those which are easier for you to solve and those which are more difficult for you. So you need to solve first those which are easier to be sure that you get that minimum amount of points which you should get because of these few problems which you are familiar with. And then you will have time to focus on the rest of the problems and try to solve them probably with some success, but no one knows for sure. And like there's a question, free navigation. I mean, yeah, if I understand the question correctly, you can use any sources to solve the problem. Just besides this option, call to friend. Other from that, you are welcome to use the textbook and so you don't need to remember all equations, which may be useful. But definitely will need understanding of the physics concepts and some practice in solving problems in general, which you are doing while working on homeworks. Yeah, you're welcome. So as you already know, there will be 6 problems. Obviously, there will be different level of complexity for these problems. Again, find those which are easier, solve them first, then you are done. Don't worry about them anymore and focus on those which are more difficult. Because from experience, I can tell you that unfortunately, students quite often manage to get less points for midterm or exam than they could get just only because of this fact that they start to focus on more difficult problems at the beginning and then just literally don't have enough time to solve the easier problems. So don't repeat these mistakes and get at least this minimum points which you can, then focus on other problems. Again, I advise you to have some tables of derivatives and integrals next to you because that could be of need during the exam, so you don't spend time looking for them in the rush. And yeah, other from that, the 6 chapters, first 6 chapters will be covered by the first midterm. Just try to be very attentive reading the problems. Don't be in a rush when you read. Try to understand it first, maybe read twice, 3 times. Be sure that you understood it correctly. And then focus and submit the answer in correct form. That's very important because otherwise it will not be accepted by the system and we will not be able to do anything with it. Okay, this is pretty much everything what I wanted to mention you about the midterm, which is coming soon. So now I think we can continue with some examples which we consider for conservation of energy. And as I remember, we stopped at this point when I promised that we will consider a bit more interesting case when force is aligned at some angle to horizon, and we will see how it affects on the previously considered case. So let me change the, oops, not like this. Let me change the camera to my slides. And now we will consider such system. So as you remember, last time we had some body on a surface, and there was some force acting on this body along the surface, horizontal surface. So our goal was calculate the speed of this body after moving distance delta x. So that we already did. Now we can make it a bit differently. So let us consider such a similar body, and so terminal speed and drag force in the 6th chapter. Yes, we do. So we mentioned about this during our online discussion. So you can double check like all these recorded discussions. So that is important part. So definitely pay attention on that. So let us assume that there is some force, but this force is aligned at some angle theta to the horizon. So here is the weight mg, and obviously will be some Fk friction force when it moves to the right. So here is reaction. And so now the question will be, in which we will try to answer, what should be the angle theta in order to get maximum velocity of this body while we move it along some distance delta x. So we are interested in maximum speed. Okay, so obviously we need to consider changing kinetic energy. So our first steps, we need to consider work done by the force, changing kinetic energy, and also work done by the friction force. So let us write kinetic energy at like final, let's call it K2 is equal to K1 plus work done by applied force plus, oh no, minus work done by kinetic friction force. So initially, speed is equal, like V naught is equal to 0. So K1 is 0. So far it's all the same. Now we need to put some already expressions for these components. So mv squared divided by 2 will be equal to positive work done by this force. So in this case, what will be the equation for the work done by force F?
F delta X.
Can you repeat, please?
Cosinus. F cosinus. Theta delta
Yeah,
X.
exactly. Because we need the projection of this force on the direction of motion. Or in other words, it's scalar product of vector, force vector and displacement vector. So it will be F times cosinus, oh, sorry, not sinus, cosinus theta. And here we put delta X. Now we need to calculate the work done by the friction force, kinetic friction force. So no, we need to subtract it, minus. How do we calculate work done by kinetic friction force?
Mu kinetic minus multiplied
here.
by
Mu kinetic times
mg sinus theta. No.
So what should we put here?
Just
in the brackets maybe mg plus f sinus theta.
minus.
Exactly, minus, because we compensate with this component of this force, which is F times sinus theta. We compensate the weight mg, and that's why our N reaction will be equal to mg minus F times sinus theta. And that is what we need to put in these brackets. Let me get rid of this. Here will be minus F times sinus theta. And multiply delta X. Okay. So this we have. Now let us express V, because we are interested in the speed. V squared will be equal to, we can take out of parentheses this delta X here, and it will be 2 times delta X divided by M, will be F cosinus theta minus mu K times mg minus F sinus theta. Yeah, didn't forget anything? Looks like not. Okay. Now we need to determine, so we can express V, just V, so can take square root of this side, but it actually not so important, because the condition for maximum V will be also a condition for maximum v squared. So we can apply. Which approach do we apply in order to define what will be the extreme value of the parameter of a function?
Derivative.
Yeah, so what do we do with derivative? So you mean first derivative?
Equalize to 0.
Exactly. So means that we have maximum point or minimum point, but minimum point in this case will be equal to 0 because velocity cannot be smaller than 0. So obviously we will get to maximum value, and this maximum value means that delta v square, like dv square over dx, dv square over dx will be, sorry, not dx. That's another question. Just dx put in by inertia. We are interested in the angle. So we're interested when will be maximum velocity in terms of the angle theta. So we want to know at which angle theta of this force orientation we will get the maximum velocity. So probably actually even better to define this like this: theta at v maximum. This is what we want to find. So obviously we need to consider v as a function of theta. So we need to take derivative dv square over d theta. And this should be equal to 0. Then we have maximum, and we will get maximum expression for v squared. Once we know maximum expression for v squared, we can easily get maximum expression for v. Okay, let us take the derivative of this function. What we need to keep in mind that for that I recommend you to have these tables of derivatives. Probably you remember this, but maybe someone remembers, someone doesn't. If we have derivative of cosinus theta, it is equal to minus sinus theta, and derivative of sinus theta is equal to cosinus theta. So this we keep in mind, and we can take the derivative. So it will be 2 times delta x over m. These guys are constants. F is also constant. We need to take derivative of cosinus theta, which will be minus f sinus theta. Here, what do we have? We have constant mu k times mg. So derivative of constant is 0. And then we have minus, and here minus f times sinus theta. Derivative of sinus theta is cosine theta, and minus gives us plus. So we have here plus mu k times f cosine theta. And this should be equal to 0. So since delta x is not equal to 0, then obviously this expression in the parentheses should be equal to 0, means that, let us write it on the next slide, that f times what it was there, let me check again. F times sinus theta. Sinus theta is equal to mu k F times cosine theta. So F and F we can cancel out. And from here, we get mu k is equal to tangent theta, because sinus theta divided by cosinus theta will be equal to tangent theta. So that is actually the condition of theta at V maximum. So this theta should be equal to arc tangent mu k. So you see that actually weight of the body doesn't matter. The angle is defined purely with friction coefficient. And that makes sense, because if we have a very small friction coefficient approaching to 0, then this angle would be should be equal to 0. We should align this friction just in parallel in order to perform maximum work, because then it will be not F times, so it will be F times delta X, because there is no friction and we don't care about it. However, if there is large friction, it could be the case that we even don't move the body with this applied force. So the static friction will be larger than the force applied. So, or even if we start moving it, it will be moving very slowly because kinetic friction is very large. So we need to decrease, by applying this force, we need to decrease kinetic friction force, and for that we need to kind of sacrifice with part of the some component, y component of force F, in order to reduce N. Then automatically we reduce kinetic friction, and then with the rest of the force F, which is this component aligned along axis X, we can pull it and reach the maximum velocity, like speed of the body after some displacement delta X. Depending on the value of this kinetic friction coefficient mu. Okay, let us maybe consider another example, a bit different, when we have some spring.
May I ask?
Yes, sure.
How did you get arctangents?
It's to get the value of this theta, you need to apply some opposite, like reverse function of tangent. So it's the way if you have the tangent theta is equal to mu k, then you want to know theta, you get the value of theta as arctangent of, it's reverse. It's like taking logarithm and exponential.
Thank you. And one more question: when we were different, I'm sorry. Did we consider MJ? Yes, take derivative. And did we consider MJ as a number?
Yes. So let's come back. So when we take derivative, we consider what as number?
MJ.
But we have M here. Yeah, here you mean this part. MK times M Sorry. Yes, it's just a number, just constant, because mass doesn't change. G is constant, and mu k is also constant. So if we take derivative of a constant, then it's just 0. So we don't put it here. We could write here like plus 0 and then plus, but it doesn't matter.
Thank you.
Yeah, derivative of a constant, if some function or some terms of the equation do not depend on independent variable over which take the derivative, then we just consider them as constant and derivative will be equal to 0. Yes, okay, so let us consider such a system. So here we have spring attached to a mass M1 and connected to some wheel with not stretchable rope. And here we have another body with M2. So let's assume that initially this system was anchored, it cannot move, and the spring is in the equilibrium condition. So it's not stretched, not compressed. Just at equilibrium condition, delta x is equal to 0 for this spring. There is some friction between this surface and mass M1, and it is described by kinetic friction coefficient mu k. Now, at some moment of time, this anchor is taken away. And because of the weight of this mass M2, it starts to move down and reaches some new equilibrium condition. Will be M2 new position. Obviously, since this rope is not stretchable, so here we will have, let's say, H, and here this guy will move to the same distance. It's M1 in new equilibrium condition. This will be also distance R. And of course, this spring will be stretched. So now the question is, if we know these masses, we know the spring coefficient K, we know the this H, distance the blocks move from first equilibrium condition. So what will be this kinetic friction coefficient? So here in this particular case, we have conversion of gravitational potential energy to spring potential energy. However, in addition, here will be some kinetic friction force, which should also be taken into account. It will perform some work, and this will dissipate the energy. So we can write that M2 times GH is change in the gravitational potential energy of the block M2 will be equal to the change of the potential, like spring potential energy, plus some work which had to be done by this friction force K. So how do we define spring potential energy in this particular case?
Kx squared into
K times H squared divided by 2. And work done by the friction force.
mu mg.
Mk times M1G. Okay, so now we define this, and we can plus no. So this is the friction force, kinetic friction
We
force.
also should multiply by h.
Yes, so we multiplied by h. So in this case, it's correct. So now we can cancel this h and this square here and express mu k. So mu k will be equal to m2 times g minus k h divided by 2 and divided by m1 times g. So what do we see here? If our mass m2 is big, obviously for a given h, if we fix this distance the body travels, mu k should be larger because m2 is in the numerator of this equation. And also m1 is in denominator, so the smaller m1, then the larger mu k should be for given h, because the friction force should correspond to some given h, like distance. Then if we consider, for instance, fixed m1 and m2, so we see that the larger h will be, so we subtract this term kh divided by 2. So the larger h, also the larger, the larger h, the smaller mu k. So means that obviously makes sense because smaller mu k will be considered as for reduced friction force, smaller mu k. So there are a question about the level of midterm problems. There will be different levels. So like this, there could be even easier and also could be more difficult. So we have some time left, and let us consider one more example, which combines conservation of energy and kinematic equations in some form. So let's have some inclined plane which goes horizontal at the end. Then we have some ground level. So here is some distance d between the end of this plane, like and the ground level. And we have some body which is going down on this inclined plane without any friction. So at this point, it will possess some velocity v, and then it will fly as a projectile and will land at a distance L from the end of this, from this edge. So let's have here axis Y, here axis X. So the question will be, from which height this body should slide h in order to land at this distance L from the edge of this ramp, inclined plane with this horizontal part. So let us think with what do we start? What first we need to define?
Maximal potential energy.
Okay, we have some potential energy. And what will be potential energy?
Equal to maximal kinetic energy.
Yeah, so we want to know the velocity. So mv squared divided by 2 will be equal, so this kinetic energy, we don't have any friction, so we will have complete conversion of potential energy to kinetic energy. So here will be mg times h minus d. You see, it doesn't go to the ground level. It stays at some distance d from the ground level. So we will consider kind of this height, which is h minus d. So in this case, this can be canceled out, and v is equal to square root of 2g times h minus d. Okay, so with the speed we figure out. So then what will be if we consider here the x equals 0, then what will be coordinate x as a function of time after this body starts to fly as a projectile? It will be this v
t minus
t. So here it will be just v times t, because this v doesn't change in horizontal direction, and this v is already defined. So it will be square root 2g times h minus d and times t. So what will be the y coordinate as a function of t? Any ideas?
Minus gt squared over 2.
Yeah, but there is
D minus.
yes, d minus, because we have this initial height d from 0. So d minus gt squared divided by 2. Okay, from here we can define when our body will hit the ground in terms of time, t. because we can set this to 0. So when y is equal to 0, so it will be this point. So from here we get t, let's call it t prime, will be equal to square root of 2d divided by g. Okay, so now we know the duration of the light. So we know the velocity in along axis x. So we can calculate the distance L. And this L will be equal to v times t prime. So this t prime, how long it falls down, times velocity along axis x. So now we can substitute instead of v our expression here, we got it, will be 2g times h minus d times square root of 2d divided by g. So here we have g and g, cancel out this. And so it will be 4 times d times h minus d. And let us write it, continue on the next slide, and take this into second power. So let's get rid of this square root. So it will be L square. L square is equal to 4d times h minus d. And split this, like open the parentheses, 4d times h minus 4d squared. And now we can get the expression for unknown h. So h is equal to L squared plus 4d squared divided by 4d. So this would be rewrite in a bit simpler form. It will be d plus L squared divided by 4d. So this is the answer to this. A kind of nice example when we have a combination of conservation of energy and kinematic equation.
Can I ask?
Yes, sure.
Why did we use d minus in y direction? I did not understand. In previous slide.
Sure. So we know that it's falling down. So y axis goes upwards. So the bar going downwards. And that's why we have minus gt squared divided by 2. However, it starts to fall from this point, which is at height d along the axis y. So we start from d minus this gt squared divided by 2. So it's kind of initial height from which this projectile starts to move.
Thank you. I understand.
Mm-hmm. Okay. Thank you for attention. I think this is everything what I wanted to present you. If you have any questions, you're welcome. Don't miss your midterm. be focused on that. What is I corresponds? Where do you see I? It's L. Yeah, I think we don't have I here. So we have time, velocity, height h, height d, t prime, which is the time of flight. And that's all. And this L is the distance from the end of the ramp to the point where the projectile will be landed. Okay, thank you very much for attention. Take care, have a good evening, and good luck tomorrow with your midterm. Hope everything will be good with your experience.
Thank you. Goodbye.
Thank you. Bye.
Bye.
Yeah, goodbye.
Thank you. Goodbye.
Bye-bye.